Last class में, if you recall, we had discussed photoelectric effect after the wave optics, and photoelectric effect, the explanation of that came up in 1905 at Albert Einstein, but that came with a couple of surprises, and the biggest surprise was that light is not a wave as suggested by Maxwell, it is a particle. But these particles were different from particles of Newton, because these particles were basically energy bundles called quantas, later named photon. One photon is basically collection of energy having linear momentum, angular momentum, energy, but not having mass. Alright? So if that is something that surprised us, there are more surprises in store today. And the next surprise is coming as not only the light that has dual nature, but every matter has dual nature. And if you find it unbelievable, then so did the teachers of de Broglie. In 1924, he submitted his doctoral thesis. He was a duke of a place called Dépy in France. He was a graduate student of English literature and history, who later decided to major into physics under the influence of his brother, who was a theoretical physicist. And he is coming up with a proposal, asking a question in the doctoral thesis. And what is he asking? His name is Louis Philippe Victor de Broglie. Now many people call him de Broglie, that is their problem, but name is Louis de Broglie. Okay? तो इन्होंने एक suggestion दिया. He asked a question in his thesis. He said that once photons, which are particles, basically which is light, which is collection of photons, which is a wave, can behave like a particle, then why particles cannot behave like waves? This was his question in 24-page thesis. Nobody believed him as usual, but he was lucky to get his doctoral thesis because a person named Albert Einstein happened to be visiting Paris at that time. He said it's a good idea that needs to be explored further. But science doesn't work on appreciations and recommendations. It needs proof. And proof to this was given by Davison and Germer. Lester Germer and Davison, they gave the proof. They were independently working on diffractions. So they found that whatever this fellow de Broglie is telling you is right. So a particle, when it is moving, if it possesses a mass m and velocity v, then it has a momentum p equal to mv. Then according to him, this particle also will exhibit a wave, and the wavelength of that wave will be equal to h over p. And this lambda is of course de Broglie's wavelength. But then there is a problem. If you come across the real life situation, think about football. What must be the mass of football? Okay, let us take 1 kg, right? H ka value is 10 to the power minus 33, that order, 6.62 into 10 to the power of minus 34, so order of magnitude minus 33. Speed of the ball that you kick may be 10 meter per second, and 1 kg ball going with 10 meter per second. So you see this lambda is 10 to the power minus 34 meter. What is the wavelength of light? 5 into 10 to the power minus 7. And this wavelength is 10 to the power of minus 34. How do you see it? That is not possible with the real life objects to see, and hypothetical assumptions will not get you a thesis and a Nobel, definitely. ओके जो उन्होंने कहा कि अब जिन्हें सोचना शुरू करते हैं कि कैसे इसको रियल लाइफ सिचुएशन से मैप किया जा सकता है. तो पहली बात यह है कि इफ यू हैव टू कम टू सम रियल लाइफ सिचुएशन, देन दिस h you can't change. This is 10 to the power of minus 33, around that. This p, if you take an electron, the order of magnitude of a mass of electron is 10 to the power minus 30. 9.1 will become 10, 10 to the power minus 30, okay. And now if you accelerate them at 100 volt, the speed acquired by them will be around 10 to the power of 7. So if you cancel now this term and this term, you get 10 to the power minus 23, and the lambda is 10 to the power minus 10 meter. But then the problem is still not over. 10 to the power minus 10 meter. This is size of an atom. So how do you make a grating if you have to do a diffraction experiment? How do you make a grating of 10 to the power minus 10 magnitude? Diffraction grating क्या होती है? On a slide you draw some lines. Supposing this is a class slide, you draw two lines on this, opaque lines. Now this is a diffraction grating. You can make many. Okay, if you make many lines on this, then you can carry out the diffraction experiment. Generally gratings are used, right? जैसे एक्सरे डिफ्रैक्शन आपको मालूम है, क्रिस्टलोग्राफी में एक्सरे डिफ्रैक्शन इज वेरी वेरी पॉपुलर. तो इस तरह की ग्रेडिंग कैसे बनाएं? बट देन देयर इज अ रेडीमेड सोल्यूशन इफ यू कम टू थिंक अबाउट इट. इट इज साइज ऑफ एन एटम. तो चूज सम मटेरियल जिसके एटम इस तरह से अरेंज्ड हो कि अरेंजमेंट ऑफ एटम गिव्स यू व्हाट? गिव्स यू अ ग्रेटिंग बाय डिफॉल्ट. अब अगर आप इस पे एनर्जी स्कैटर करते हैं, सपोजिंग एक्सरेज इस पे डालते हैं, तो आप जानते हैं कि जब भी ये ओपनिंग जो होती हैं, इनका ऑर्डर अगर मैं कहूँ कि बी है, इफ यू यूज द डिफ्रैक्शन फार्मूला और यू यूज द इंटरफेरेंस फार्मूला, इन एनी केस you get lambda by b. But this diffraction, interference, scattering with proper peaks at one place, valleys in one place is exhibited not by particle, they're exhibited by waves. अगर मैं particles को scatter करूं तो they will come back at a definite. If I throw something at I, it will come back at R. If elastic collision, otherwise the angle will become smaller because there will be a loss in velocity. But when I'm putting waves, then I know that there are definite peaks and there are definite valleys. For what conditions, that you know. तो इसमें जो जरूरत पड़ेगी एक बात की, ब्रैग्स लॉ आप जानते हैं, तो मैं पहले से उसके बारे में बात कर लेता हूँ. ब्रैग्स लॉ इज अ लॉ फॉलोड बाय waves that is used in X-ray diffraction using crystals. So if the crystals are arranged like, the atoms are arranged like this in a crystal, and let us say you make the light incident from here and here, so some light will scatter from here. This angle is called theta, this is called the glancing angle, and ये angle जो होता है बीच का phi, this is called the scattering angle. This is theta, this is phi, and there is a symmetry, this is theta, so the light will come here and will scatter from here. If the separation between this plane and this plane is d, then it is easy to show that if I drop a perpendicular here and if I drop a perpendicular here, then you can say this distance and this distance are equal, but this particular wave has traveled this much extra. Okay, अगर ये 90 डिग्री है, ये भी आपने परपेंडिकुलर डाला, ये 90 डिग्री है, तो मैं आपसे जानना चाहता हूँ कि if this is d, if this is d, this is theta, so this is 90 minus theta, so this is theta, so this distance will become equal to d sine theta, this distance will be equal to d sine theta, so the path difference to d sine theta, when it becomes equal to n lambda, you should get what? You should get maximas. But this law, if followed in this way, will be followed definitely by waves, and X-rays are waves. So if you diffract X-rays using crystals, you get definite maximas. If you rotate, you get the diffraction discs. You get that. लौट के आते हैं जहाँ पे हम थे. तो अब ये प्रॉब्लम तो इससे सॉल्व हो सकती है कि you use some material to do this. लेकिन डी ब्रॉय की जो हाइपोथेसिस है, इससे जो रिजल्ट हमारे काम के हैं, पहले मैं वो बोर्ड पे सम अप कर लेता हूँ. हम लोग कह रहे हैं लैम्डा इज इक्वल टू h अपॉन m v, दैट इज h अपॉन p. नाउ यू नो एनी गिवन डे वी कैन डू व्हाट? वी कैन राइट इन प्लेस ऑफ p, हम क्या लिख सकते हैं? वी कैन राइट रूट 2 km, where k stands for what? K stands for kinetic energy. Next to that, lambda equal to h. Now, if a charge particle of charge q is accelerated with accelerating potential v, then this k can be replaced. This can be replaced as q into v into m. तो तो अब अगर यहां से आप कुछ फॉर्मूला हमेशा के लिए बनाना चाहें तो दैट कैन बी डन. लेट अस डू इट. लैम्डा, you can see h is 6.62 into 10 to the power minus 34. If I talk about an electron, the charge of that is fixed, the mass of that is fixed. The only variable is V, that is voltage that you apply. So you will say fine, let us remember the result, 12.26, 12.27 divided by root V. This will give you the wavelength in angstrom. For what? For electron. Similar experiment if you do for proton, you will get 0.286 divided by root V angstrom. If you find out lambda for deuteron, okay, that is 0.286 divided by root V, you will get 0.202 divided by root V angstrom for deuteron. If you do it for alpha particle, then you will get 0.101 divided by root V in angstrom. If you do the same thing for a neutron, your answer will be 0.286 divided by under root of kinetic energy in electron volt, because there is no charge on this, but Q into V. आपको मालूम है कि this will convert it into kinetic energy in electron volt. So we are writing kinetic energy in electron volt. If it is a football that you kick, then this formula will hold. And if I tell you a bullet is traveling, the mass of the bullet, or let us say kinetic energy of the bullet is given to you, then you can use this formula. If I talk about a gas molecule, then gas molecule has got a mass. And you know the speed of the gas molecule is given by root 3 by 2 kT. So from there you can find out what? You can find out the energy and substitute it. आपको यही करना है. एनर्जी को किसी भी तरह ढूंढ के लाना है, यहाँ सब्स्टिट्यूट करना है, या मोमेंटम को यहाँ सब्स्टिट्यूट करना है, और जिनमें Q है, M है, ये फाइनाइट हैं, ये कुछ रिजल्ट हमने याद कर लिए. तो दिस इज इट. तो ये जो बात कह रहे हैं आपसे कि इलेक्ट्रॉन्स, प्रोटॉन्स, न्यूट्रॉन्स, इवन दे शुड बी एग्जिबिटिंग द वेव नेचर. बट जैसे मैंने कहा कि फिजिक्स इज मोर अबाउट प्रूफ्स देन सेइंग थिंग्स. ओके, so the proof to this was provided in 1927 by Davison and Garmer. They provided the proof for this, and at the same time they worked in New York. G.P. Thomson was working in Cambridge, London, where he also did a similar experiment, but he used a different setup. So independently they showed. Incidentally, G.P. Thomson was son of J.J. Thomson. J.J. Thomson got a Nobel for what? For discovery of electrons as a particle. Son gets a Nobel for showing that electron is a wave. That's the beauty of science, that nothing is permanent here. Okay. मिटा सकता हूँ ये सब. अब जो बात मैं कर रहा हूँ आपसे, perhaps this is one of the most important for your school exams and board exam, that is the Davison and Garmer experiment. ये Davison Garmer experiment आपसे क्या कहता है, इसके बारे में हमें थोड़ी सी बात करनी चाहिए कि what is the feeling that is conveyed by there, or message conveyed from there. Bragg's law is a law which is followed by waves. We know this. But now they are putting this to test using accelerated electron. तो पहले हम बात कर लेते हैं what is the setup. Davison Garmer experiment. तो इसके अंदर 3 basic components हैं. First is electron gun. So they took a filament, and with this filament they heated up a cathode. This is the filament F, and with this filament you can heat up the cathode so that electrons will boil off easily. Now you give a negative voltage to cathode. Of course negative should be given to cathode. Electrons जो यहाँ से निकल रहे हैं, you make them pass through a collimated anode. So this is basically an anode with a hole in the center. So ये collimated anode क्या करेगा? This will make sure that the parallel intense energetic beam of electron is emerging from here. और ये जो आपने यहाँ तक बनाया है, ये पूरी चीज़ कहलाती है इलेक्ट्रॉन गन, बिकॉज द पर्पज ऑफ दिस इज टू गिव यू द इलेक्ट्रॉन्स. You can join this plus to the anode so that QV part will be taken care of. Then what they do is they take a nickel crystal. They cut it like this and they place on the path of this. This is a nickel crystal. ये जो distance है between these two acid, this is 2.15. This capital D is 2.15 angstrom, and the small d is equal to 0.91 angstrom for nickel. Now let us see what are we expecting or what are we looking for. You are putting this beam of electrons on this. Now these beams will get scattered from here. If you are looking for what? If you are looking for definite maximas and minimas, then you can do what? You can put here a detector. ये detector दो तरह के हो सकते हैं. They can be ionization chambers or they can be Faraday cups. Okay, ionization chamber हो चाहे Faraday cup हो, ये क्या करेगा? These diffracted electrons, scattered electrons will be gathered at different angles, and you will try to see that at what voltage and at what angle you are getting the maxima. इसमें कोई gas भर देते हैं, they fill up some gas in this, and these scattered electrons, when they go inside the gas, they cause ionization. So the amount of ionization that you get, अगर electrons ज़्यादा हैं तो ionization भी ज़्यादा होगा, and that ionization current can be read by a galvanometer, or the collected charge can be, calculated कि किस केस में collected charge ज़्यादा आ रहा है. So they did this experiment by varying voltage here for different voltages, 40 volt, 45 volt, 47 volt, 54 volt, 60 volt. They plotted the polar charts, okay? And they found that when the voltage is around 48 volt, they got something like this. What is this? Let me tell you. अगर आप इसको simple graph के form में देखें, तो आपने एक देखी बात कि when the angle of scattering, ये angle जो है phi, when this angle is 50 degree and the voltage is 54 volt, you get the maximum ionization current. That is, maximum current is obtained when theta or phi is equal to 50 degree and the voltage is 54. Now these are polar charts. Polar charts are between the incident beams. For different angles they are seeing the current. So there is no distinct maxima here. ये कुछ बढ़ रहा है when it is 48 volt. But when the voltage is 54 volt, you find that you get a sharp maxima that is corresponding to the scattered beam, that is this beam, and this incident beam. When this angle is equal to 50 degree, you are getting the definite maximum. If you increase the voltage further, ये circular polar charts होते हैं जिसमें for all 360 you can make, 360 की ज़रूरत ही नहीं है. If you go 180 you can get all the answers, or rather 90 you go, you will get all the answers. So यहाँ से अगर आप देखें, if I increase it to 68 volt, again I find that this becomes like this. That is, there is no maxima that is observed. So a definite direction, definite voltage, you are getting a maxima. अब ये बात clear है. You can see that this angle we defined as phi. Glancing angle जो हमने देखा था या जो लिखा है, आप देख सकते कि glancing angle is phi, और इस केस में जो scattering angle है that is equal to theta. So you can see for yourself that 2 theta plus phi ये किसके बराबर है? 180 डिग्री के. तो 2 theta will be equal to 130 degree. So theta will be equal to 65 degree. So you have this result with you. Now you go to Bragg's law and use the Bragg's law to find out the lambda using Bragg's law. तो Bragg का नियम से अगर आप lambda निकालें तो आपके पास में आता है D, that is 0.91 into 2 into sine of 65 degree divided by what? N is 1, सो अगर आप इसको d sin theta 2d sin theta is equal to n lambda से वर्कआउट करते हैं तो you get an answer that is 1.65 angstrom. Alternatively, if you do it with this 2.15 data, that is d sin phi, that is 2.15 sin 50 degree, still you get 1.66, right? So the scattering will take place not only from these planes, it will also take place from the nearby planes. So for that also, if you see, so this is what Bragg is telling you. But Bragg's law is valid for waves. But you are dealing with what? You are dealing with electrons. So if you are dealing with electrons, there has to be something better now. So de Broglie क्या बोल के गए? वो बोल के गए कि भाई देखो ऐसा है, when the lambda of electron, his formula is what? His formula is under root of 150 divided by V. Under root of 150 is 12.27. So ये V आपके पास है, distinctly you have the V, that is V is equal to 54 volt, and now if you do the calculation you get 1.65 angstrom. That means the de Broglie's result is telling with the result given by the Bragg. So indeed what he is telling makes sense, that electrons indeed are behaving like waves. The 1929 Nobel was given to de Broglie for matter waves. 1937 Nobel was given to Davison, Germer and Thomson for showing that electrons exhibit wave properties. The Thomson का experiment था, that was like this. What he did, he accelerated electrons with a very high voltage 50 kilovolt, and this accelerated beam of electrons was fired on gold foil. और उसके पीछे उन्होंने, he kept the photographic plate, and on that he saw the scattered electron diffraction pattern, and he compared this with X-rays, and he found that the both tally with each other. Only thing, the intensity for electrons was less because they carry lesser energy in comparison to the X-rays which are higher energy. Then de Broglie, whatever he said was not only to electrons only. Then they extended this to many other things, like they used helium molecules bombarded on lithium fluoride, and for that they got a distinct pattern like this, maxima minima pattern. The neutrons on common salt, NaCl, they fired the energetic neutrons on sodium chloride and they saw the diffraction pattern. So they said if the circumstances are right, that is this mv is within the limit, then you can see that matter behaves like a wave. So matter has dual nature. We all have dual nature. Your behavior with your best friend and a person who is just introduced to you is very different. You take the best friend for granted, but a person is just introduced to you, you try to be, extra polite, extra